Hi, my name's Dr. Phil Winder, and I'm the CEO of Winder.AI. As you know, we operate in the AI space. We deliver RL, ML, and MLOps consulting and development, and these talks are all about the work that we do. This month, I would like to talk about our work that we did with Pachyderm to investigate the differences between two competing data engineering products. One is Databricks, and the other is Pachyderm. In this talk, I hope you will get some appreciation of what these two tools are designed to do. This talk is going to be approximately 20 minutes long. And if you're watching this live, then actually I must apologize. This is a recording because I am away at a conference. So unfortunately, I won't be able to answer any questions this time. But of course, you can reach out to me via Winder.AI website or any of the other any of my social profiles, and I'll be happy to answer any questions. Okay, so let's get started. So the whole goal of this talk is to compare two very popular commercial general purpose data engineering technologies, and they're very popular in industry. They're both used heavily. We see it a lot in our work, and we also use it a lot as well. Consider ourselves experts in Pachyderm, but we have also used Databricks for quite a lot of our engineering work as well. One of our interests in MLOps, so one of our things that we like to focus on, is the idea of lineage, because we think that lineage and provenance is a really important topic in machine learning and is necessary for even medium to large size businesses, purely from an efficiency perspective and also from a governance perspective. So I'm particularly interested in lineage. This is based upon a white paper that we wrote last month. You can find that on our website. That's got the full details in there. So if you're interested in the details a bit more, because I'm only going to present a summary here, then please do read that white paper. So in this talk, I'm going to split this up into about 8 different sections, investigating different aspects that I think that are important in MLOps and machine learning, but also the sections that highlight the differences between these two products. So one of the main differences is the intended use cases. So I'm going to cover that right at the start. But then I'm going to start digging into some really technical topics. So how it handles structured and unstructured data. Lineage, as I mentioned before, how both fare when it comes to lineage. Incremental processing for efficiency purposes. And one of the most important things actually is the developer experience. And there's some quite substantial differences here, which we'll talk about later. Integration and processing graphs. So this is all about how well and easy is it to integrate these products with other products, because these things don't live in a vacuum. And the processing graph, the graph that defines what processing is going to happen, the ability and ease to define that is really important. And finally, I'm just going to provide a high-level overview and recommendations what these two tools are good for. So Databricks is a company and a product. They offer a suite of tools that aim to be a general purpose ML and data science platform. At its heart, Databricks consists of Apache Spark. So they were the original developers of Spark, and that is used for most of the heavy lifting that is done within the Databricks ecosystem. The key components are, or at least the key components that are most relevant to this talk, are Data Lake and Delta Lake, not Data Lake. Delta Lake is the versioned file storage that the Databricks ecosystem exposes, and that's what brings you some level of lineage and versioning. Spark obviously is at the heart. That's the thing that provides you with scalable pipelines to perform processing tasks. And one of the interesting thing about Databricks is that they have managed to secure deals with all the major cloud vendors. to host managed versions of their software inside the cloud vendor's ecosystem. Hardly any other companies have managed to secure those deals, so it places them in quite a unique position. There's a bit of a captive audience there if you're already working with one of these cloud platforms. It's a very low barrier to entry, and its primary use case is analytics workloads, and that is something that we're going to see time and time again throughout these slides. For Pachyderm is a general purpose scalable data versioning solution that also consists of pipelines. So it doesn't have separate names for its products. It's Pachyderm, as you know, Pachyderm is both the data versioning and the pipelining solution. It is general purpose enough to use to be used for most parts of the ML lifecycle. And its key components are the version data layer. It's got really strong versioning credentials here. It's a Git-like experience, but it's also got versioned pipelines as well, and they integrate very tightly to that data layer. The interfaces and the opinions are very open and very light, and it is Kubernetes or cloud or container native, so it makes it quite easy to use from an MLOps perspective. Pachyderm's use case is general purpose computation with Lineage. So I would say that the vast majority of customers are using it for heavy data engineering tasks that require Lineage. But you can, as we demonstrate in some of our examples, you can use Pachyderm pipelines for a lot more of the ML lifecycle, including, you know, pushing things into deployments and updating model registries and things like that. So with regards to those use cases, the two products tend to focus on a particular type of data. Databricks focuses on structured data, and that is stored inside their product called Delta Lake. The format of that data is very tabular. It's basically like a database structure, you know, a row column like structure, and it expects your data to be structured in that way. There is scope to include a lot of metadata alongside that structured data, which is really useful for downstream use cases. And Spark also comes with a lot of connectors to allow you to easily ingest data from other sources, which is actually really useful because a lot of the time that is the bulk of the job here is moving data about, and Spark's got some really good support to ingest that data. Yeah, and obviously Delta Lake itself integrates tightly with Spark. In fact, it's hard to separate the two things. You probably wouldn't, you don't see Delta Lake being used by itself, for example, because it's so tightly integrated with the rest of the Databricks ecosystem. Pachyderm, on the other hand, focuses on being as general as it possibly can be. So it can handle structured data, just like Delta Lake can, but its primary purpose is to handle unstructured data, and that data is stored in a blob-like format. So you can use structured data in the sense that you can pass it JSON objects or CSV files or structured data like that, but they are fundamentally stored in a blob-like storage format. One of the really nice things about Pachyderm's data expectations is that it's generally exposed as a POSIX-like file system. So when you're in a notebook or in a pipeline, you just operate on the files as if they are part of your file system. So it's a really nice, simple user interface there. And this can scale to petabytes of data because they do focus on unstructured data. They have put significant effort into ensuring that it scales to large amounts of unstructured data as well. Sorry, I got a bit of a sniffle. In terms of Lineage and versioning, they handle it in very, very different ways. So firstly, Databricks on the left-hand side there, this persists, Delta Lake persists its changes in something that they call a transaction log. Basically, it's a file that logs all of the things that have changed in your most recent commit. So it's a metadata-based approach to storing changes in data, and those data are compressed into Parquet files. The changes that are registered are done on a row level. So the deltas are done on a row level. So if anything within that row changes, then the whole row needs to be updated. And this is one of the principal reasons why Delta Lake cannot really work with unstructured data, because if you're forced to store that unstructured data in a row column like format, and therefore, you know, you even if you have you know, a massive JSON blob, for example, if you update one character within that JSON blob, it effectively updates the whole row, and therefore you need to store that whole new row again. It also has fundamental limitations on the amount of time in which you can go back to previous data. So the transactional data by default is only stored for 30 days, and the raw data, the actual Parquet files, are compacted every 7 days. So that means that you can only reliably go back 7 days to past data. So that's problematic in use cases that require lineage for a longer period of time. The reason why they do that is because the compacting helps to reduce the storage burden here, so that it makes a more efficient use of space. And also these analytics workloads, these processing workloads that Databricks and Spark has been designed for, they're generally completed within 7 days, and therefore, you know, they don't need to go back any further. For Pachyderm on the right hand side, you get a much more Git-like experience. It's a really nice developer experience because it's so similar to what we use on a daily basis with Git. It stores its deltas or its diffs via chunking. Basically, even if you've got a binary blob, it chunks that binary blob up into little bits, and it checks to see if those little bits have changed. And if they have changed, it only updates those little bits. It doesn't update the full file. So you could have a huge video file in there that's several, you know, tens of gigabytes or whatever, and it will only update the small chunk that has been deleted or whatever. So you get a really efficient use of storage, in the sense that you're only adding new data when it really is new data. You're not duplicating, or you're hardly duplicating any data at all. These changes are immutable and they persist forever. So there's no timeouts or anything there. So obviously you get time travel out of the box. You can go forwards or backwards to previous versions, but you also get useful Git-like workflows like branching as well. That can be really useful when it comes to data. And one of the most important differences here is that because the commits are stored in this diff-like manner, that makes the lineage really strong. So with the Databricks on the left-hand side, that's metadata driven. Therefore, I could just go in and accidentally delete one of those metadata files, and you've completely lost and trashed your lineage for everything at and before that point. You can't do that in a Git-like experience because, firstly, it doesn't allow you to do that. And even if you were able to do that, it would be so obvious because the whole commit tree would be destroyed. And you can, you know, restore back to backups if that's what you're interested in doing. So it's a slightly stronger, more enforced lineage than a metadata lineage than Databricks provides. If you're interested more on this topic, then I suggest you have a look at some of my previous videos on lineage and versioning. Incremental processing is important because you don't want to waste CPU time on things that have already been completed. So one of Pachyderm's key use cases is the incremental addition of new data, and you control what level of sharding, I guess, you use within your data. They have this idea of a datum, which is customizable. And so you can kind of tell it to work on like bunches of files or individual files or combinations of different files. And every time Pachyderm sees one of these new datums, then it will send it through the processing chain. The pipelines will only process these new datums. So if something has already been computed, it won't recompute it, but it will appear at the output as if they have been computed. And therefore, the storage of not only the data layer, but also the pipeline layer after that, only the new changes are stored. On Databricks' side, it relies on you specifying how to shard in your Spark code, in your Java Spark or Scala Spark code. And that is actually a really difficult thing to do. Sharding, data sharding and memory management in Databricks is really hard because it's so hard to predict what Spark is going to do and how much memory it's going to need given the code that you have written. Because of that, if by default, you don't specify any sharding, then it must reprocess all of the data, even if only a small amount of that data has changed. It does have checkpoints to checkpoint the process in case of failure. And Spark Streaming also has the idea of triggers as well, which allows you to trigger on new data. But it's all quite complex. It's all quite hard to manage, and it's principally driven by your Spark code. It's not as simple as Pachyderm. So this has a bit of an impact on the developer experience. But yeah, before we get there, let's talk about installation methods. So traditionally, Spark was deployed on things like Hadoop or Mesos. Now, those two technologies are largely deprecated. And if you were to install it on another orchestrator, a more modern orchestrator like Kubernetes, it's certainly not straightforward. Spark Operator is somewhat useful, but you're still effectively packaging whole Spark applications into into a pod effectively, and because of that, it still makes it very hard to do things like parallel processing and sharding and memory management and stuff. On the other hand, though, because Databricks is found throughout the landscape, there's lots of managed options. You can go to any of your cloud vendors and get a managed option out of the box, which is nice. I mean, it's nice. Yeah, it's very easy to get started in that way. From a developer's perspective, you are mainly interacting with Spark on a local level. You quite often use local mode. So Spark is basically just a jar, and you can run that in local mode to develop and test your code. And it does this via a CLI experience. You use the CLI to submit code to your local system. When it comes to attempting to push that to a remote system, then again you have to push your jars up to that remote orchestrator, which again can be quite a complicated thing to do depending on how you're orchestrating Spark in the first place. Yeah, so I'm not a particular fan of that because it's, ideally you don't really want to be giving developers sort of direct access to a production cluster of any kind. It's not repeatable. It's not tracked. There's no lineage there. It's just people randomly pushing stuff to clusters. Principally, the code that you write is in Java or Scala. That's the language that the Databricks ecosystem has been developed in. There are Python and R wrappers for Spark, PySpark, for example, but they are wrappers of the Java API. And one of the biggest issues with that is that when you run your code and it inevitably fails when you run it for the first time, all of this, like something as simple as the stack traces, they're all in Java. They all spit out Java stack traces, and therefore in order to debug what went wrong, you have to parse and investigate that Java stack trace, which means looking at the Java code. And so even though you're working in Python, you're basically working with a Java API. So you need to know the Java API in order to work in Python. The only benefit that it really gives you is that it gives you access to the rest of the Python ecosystem at that point. If you've got external libraries and tooling that you rely on that is in Python, then I guess that's what it's for. That's great. But developing Spark applications in Python is, I'd not recommend it actually. Just go straight to Scala and bite the bullet and learn Java. So for Pachyderm though, because this is a very container native, cloud native, Kubernetes native like application, it's very lightweight. You can run it as a binary, you can run it in Docker, you can run it on your local system, you can run it in the cloud, and it's all effectively running it in the same way. It also has some really nice lightweight interfaces. Like I said before, on a low level, you're principally operating against a file-like system, a file system-like thing. And therefore, it's very easy to interact with from any language. And because you're working in containers, it means you can use any language. So pick your language of choice. Very flexible, very general purpose. When it comes to other tools, one thing that the Databricks collection does have in its arsenal is the rest of the tools that are quite useful for other parts of the MLOps lifecycle. So, for example, Databricks are the primary developers of MLflow, even though it's open source, and that comes sort of pre-baked into the Databricks suite, and that's a very solid choice for model and experimentation management. There's some other tools in there as well. But to interact with any external tools, then you need to, use interact with it from within your Java code, which again, because of the complication of the processing graph, which we'll come to in a second, and the complications introduced by the sharding and parallelizing methodology that it uses, it's actually a little bit more difficult than you'd think. You end up with loads of duplicates, for example. And it's obviously less flexible because you're forced to use a single language in a single way. So if your tool, interfaces via a Go API or a Python API, you're going to have a little bit of a hard time integrating that with Spark. On the Pachyderm side, it's very flexible because you can run any code in your container, any languages, as we've already mentioned. But because of the way in which you can construct the processing graph, it's quite easy to specify extra steps in that graph to sort of very quickly and in a very lightweight way, even just using like a bash script or something to push that change, push that update to an external tool. We've got some demos floating around where we've integrated Pachyderm with MLflow, for example, and Seldom Core. So check out those if you're interested in that. So when it comes to specifying the DAG, I think actually this is when you're doing sort of general purpose ETL or processing like jobs, specifying the graph, the processing graph that you are of the workload that you're trying to operate on is one of the sort of the crucial aspects of doing development here, because all of these processing jobs can be specified as a graph. And when you do so, the processing becomes a lot easier to follow, a lot easier to understand, and a lot easier to optimize as well. In Databricks, the DAG is entirely controlled by the Spark code. And that's fine, but it adds quite a significant layer of obfuscation there, because it is optimized by the compiler before it gets sent off to actually run in the cluster. So it goes through this phase of figuring out, optimizing that graph before it gets submitted, and therefore it is quite hard to control the order in which that graph presents itself. Another major aspect is that because of that, it makes parallelization really, really hard, because you can control the level of sharding that happens in Spark, but because of all of the optimizations that happen at at compile time, and also the lack of clarity in the graph in the first place, because you're just writing code, it becomes incredibly difficult to predict how much memory and how much CPU a particular piece of code is actually going to take. And so in effect, what that means is that to control the parallelization, you basically have this sort of number that you have to just tweak up and down until you and try it and try it and try it and try it again until you get to a point where you have the performance that you were expecting. It's a very labor intensive way of defining parallelism here. Another important aspect is that Databricks or Spark graphs are computed lazily. They only compute when the output is requested. And again, it depends on your philosophy here. That can add significant delays. If the end, if you're trying to update some end process or some end API or some end product, then that end product or process needs to request it before it even starts the calculation. So obviously there's a delay there because it has to go through all the computation. And that could be a problem in your use case. It also requires an external scheduler if you're wanting to run this in batch. It won't just run on a schedule. There's no scheduling mechanism in Spark. You have to use something external like Airflow to trigger the executions to occur. Or you can use Spark Streaming, which has the idea of triggers. But that's it's slightly separate. It's a separate API. It's a slightly separate product. For Pachyderm, the processing graph is specified by configuration. Effectively, for every stage in the pipeline, you define its inputs and outputs via a simple manifest, and that ultimately defines the full processing graph. It's very simple. You have full control over it. It's very clear what the graph is going to look like when you make those changes. And the parallelization is very easy because it's controlled on a datum level. Basically, you can specify how many things you want to process in each thing and specify the level of parallelization that you require. So nice, simple, easy to understand. Really nice properties. There's a couple of other cool features. One is that, like I said, Databricks is quite a large suite of tools. It's a collection of tools. It's got notebook hosting in there. It's got lots of SQL related tools because it's designed for analytics workloads. It's got a really well-regarded SQL query optimization layer called Photon, which can speed up your SQL queries if you're a heavy user of that. It defaults to batch, but it can also do streaming workloads via Spark Streaming, and there's a few other aspects to it as well. On Pachyderm's side, they also have notebook hosting, and they also have quite a sophisticated S3 API that you can expose from the end of your pipelines, which allows other systems or applications to interact with the data via an S3-like interface, which is really useful actually for integration purposes. Pachyderm also has, it defaults to operating in batch, but it has a streaming capability via something called spouts. And it's another sort of layer of configuration in the configuration file to define it as a streaming process rather than a batch process. So actually, it's very easy to switch between the two. It's almost a one-click like experience as opposed to Spark Streaming and Spark, which are very different APIs. So trying to summarize all of that up, Databricks is entirely designed for analytics workloads. And one of the key the key sort of implementation, one of the key facets of that design is that the output drives the computation. It's the output that defines when the computation happens and how it happens. So that means it's really good for SQL like workloads, for very structured data, and if you're a fan of Java and Scala. Pachyderm, on the other hand, is much more general purpose. The input drives computation. So as soon as it sees some new data falling into one of its data repositories, then that will drive the pipelines from start to finish. So that means it's really good for unstructured data. If you're using unstructured data for any sort of general purpose machine learning or anything like that, it's a really good choice. It's got really strong lineage guarantees and really solid lineage and provenance guarantees that you can use well into the future. So it's got some really strong governance credentials as well. It's very general purpose. It has some very open interfaces. It's very easy to work with, and it's cloud native, which I personally prefer. Prevents some of the lock-in that you can get from using some of the cloud vendors' managed services. So in terms of what's the right choice for you, I would use the use case as the main driver. If your use case is analytics, then I would certainly consider Databricks because it's got some really solid managed options in the cloud vendor in the cloud vendor of your choice. There is some significant lock-in there though, because you're locked into Java. You have to use the Spark API. Quite hard to transfer that processing out if you ever decide to change systems. But it really has been designed for analytics, and so it will probably satisfy your requirements. For Pachyderm, however, again, if you've not got an analytics workload, then I would suggest that you consider using Pachyderm. It's really nice to work with because it's so container focused and it's so unopinionated that you can work with it in any way that you want to work with it. Okay, and that's the end of the presentation. As I said before, this was based on a white paper that we have on our blog. So if you're interested in digging into the details there, then please browse to Winder.AI/blog or just Winder.AI and follow the links. You can find the schedule for future talks at Winder.AI/events. And of course, you can email me at phil@Winder.AI, and on Twitter and LinkedIn. I primarily use LinkedIn, but I'm known as Dr. Phil Winder on there. If you want to reach out or connect with me, it'd be great to connect to you. With that, I think I'll leave it there. So apologies again. I'm not actually here. This is a recording. I'm away at a conference at the moment. So if you've got any questions, then feel free to email. If you have any projects that you'd like any help on, any RL, ML, or MLOps projects that you need support in, then definitely reach out. I'll be really interested in talking. And I'll see you all again next month. Thank you. Thanks a lot. Bye-bye.